in the commutative algebra, we can start with elementary concepts modules. Elementary concept modules. Elementary concepts in modules. Introduction, definition, examples, submodules, and question modules we are learning here. And homomorphism, fundamental theorem of homomorphism also you have to learn here. So in the aims and objectives, so in that we know that the definition, some examples of the module over reading, submodule of question, module of the module, and the creation elementary properties, the concept of the homomorphism of the module, and certain important towards the homomorphism. So the fundamental theorem of homomorphism and certain homomorphism theorems also you have to learn this one. Definition of the examples of the modules. Definition of the examples of the modules we are taking here. So in the definition, in the we give a formal a module definition we are taking here. A module over a ring provides certain important examples, certain elementary properties of the modules are center that by the ring always mean a commutative ring with identity. We shall begin with the following. One definition we have to take here. In definition I'm writing here, let R be a ring, an abelian group, and abelian group M comma plus. So R be a ring, abelian group M comma plus is said to be a left R module and left R module or left module over R. So left module R module or left module over R also we have to take it. If there is a map, A comma X stands to AX of R into M, AX R into M by satisfying the following properties for all AB belongs to R, XY belongs to M, we have to take here R into M into M satisfying the following properties for all A comma B belongs to R. District's first citizen and X comma B belongs to District Election Officer, Election RO, District Administrator, A into BX. So we can write this is AB into X also. AB into X also, AB into X also, right? A into X, AX plus B into X, BX I'm writing here. Third property, A into X plus Y. That is I'm multiplying the AX plus AY. This is A into X plus B into X. Then I'm A into X. This is associated like that. And then on the fourth property I'm taking here. Ix is equal to X. Then where I is the multiplicative identity now. Where I is the multiplicative identity in R. We are taking this. So or we know that the module left R module is here. The ring R module can be defined. Ring R module can be defined as an abelian group. M comma plus a ring R module can be defined as an abelian group M comma plus together. So together, which means in addition, we are taking as the map. What we have taken here, a comma x means that is AX. So therefore, m into r stands to m I am taking here. And then the property, you know that xa into b is equal to x into ab. So xa into b is equal to x into ab. Also right here, x into a plus b is equal to already written xa plus xb. Then x plus y into a is equal to xa plus ya. So therefore xi is equal to x. So additive properties are here. Then the identity property here. So therefore xi is equal to x for all. We are taking here all these values in x comma y belongs to here. So this is and also this is a b belongs to r. This is a b values belonging to r. Any left we are taking here we are taking here. Any left R module can be made into a ring R module and defining as a x a is equal to x a is equal to ax. For all x belongs to M and a belongs to R. So all the values are we are taking here. Similarly, a ring module means is a left module. My mandate into left R module. Ring module is left R module here. So this kind of module we know the result, what is the value in left arm. So left arm, what is the value here? It is a value in right module also. That is a right module also, you can that is a vice versa, we can take in it. So we concentrate on the left arm modules throughout the entire this one. The left arm module simply you can take the R module. So certain so many examples here to prove the following elementary properties. How we have to prove here. So note that the additive operations with the R will be denoted by the symbol addition and additive M and in R will be denoted by the symbol 0 here. So now we can take the one theorem here. Let R be a ring M on R module in the following hold for any x comma y belongs to M, a comma belongs to R. Xy belongs to R, a comma belongs to R. So that the first condition we are taking 0 x is equal to 0 and a0 is equal to 0. A into x minus is equal to ax minus a by so x is 0 into 0, 0 into x minus is equal to x minus y. A minus b multiplying ax minus bx. So we have to prove this one, these conditions here. You know that first in that first 0 x equal to 0 is 0, 0, 0. The right hand side in the additive identity. So therefore m while 0 at the right hand side, the additive property in G. So the m is 0. So since we are going to take the conditions here. Since 0, 0 plus x is equal to 0x, 0 plus 0 into x is equal to 0x plus 0x. We are multiplying the same, but 0x is equal to 0. But we have to multiply both with the x. 0 into x is 0, 0x into 0. But the same has been value is 0. The second condition 0 plus a into 0 is equal to a0. In A, I'm taking A into 0 plus 0. A0 plus A0 also is a 0. So we have A0 is equal to 0, but we have to multiply the same here. The third condition, X is equal to A into X minus Y plus 1. Plus Y and minus Y cancel here. So therefore, A into X minus Y I'm taking here plus AY. So this is A into X minus Y I'm taking here plus A into Y. A into X minus Y I'm taking, then A plus A into Y I'm taking here. So therefore, A into X minus Y, that is I'm writing AX minus AY. So my minus AY plus Y should cancel here. So there is a condition of the same here. AX is equal to A minus B plus BX. A minus B into X is BX. Hence A minus B into X is equal to AX minus BX. The conditions are satisfied here. The theorem. Let M comma plus let M plus be in a Abelian group. And this is the ring of integers. X belongs to define of inductive as follows here. Nx is equal to 0, n minus 1, x plus x minus n minus x. The first one is n is equal to 0. This one. This one n greater than 0 is equal. If n less than 0. So therefore m is the module with respect to the above map of m into m we are taking here. So we are taking here. Now we are writing this one modules here. So this is the modules of we are taking. This is the modules of we are taking here. So the proof. Note that the definition Dx, sorry, the definition of Nx is the same of the casual languages. You know the simply is equal to x plus x plus x plus and so on plus x up to one n times or the until the nth time we are nth is the positive integer. Then I am taking minus x minus x minus x and so on minus x. This is also n times n thing. So that is the first one is n is positive, the second one is n is negative. Details of the proof of the sheet. This is M is a R module. Left to this is R is the module here. So this one the any abelian group, all the conditions will be satisfied, can be considered as module here. On the other hand, module is a primary abelian group. So therefore, we are taking here theory of modules and theory of abelian groups. Modules and abelian groups are at most same. The sense of the study of the one of the implies, so these will be the better appreciated. So closely understanding the we are understanding the theorems here also. Now abelian group what we are taking here m plus addition and set end abelian group of m plus and set and m plus and all endomorphism of also m plus forms a ring under the operations, but not necessarily. It should not commutate. It's not mandatory. Not necessarily commutative. Means a plus is equal to b plus a. It's not mandatory for this one. So therefore, I'm writing here f plus g into x is equal to f of x plus g of x. F equals gx. F into g of x I'm writing. So if you freeze in our module from the above from this theorem, the homomorphism of this one R into end. End also implies endomorphism also implies. So therefore the converse of the this thing is also satisfying the figure. Mhm. Let M plus be an abelian group. Any abelian group or any ring here. Suppose there is a homomorphism we are taking here. P and M plus P and M plus we are taking here of rings. The M can be the made of R module defining here. Ax is equal to. So therefore Ax is equal to T into A into X for all A belongs to R. For all A belongs to R and X belongs to M, we are taking here. Here, proof this one. This is a straightforward verification. This is a straightforward already earlier theorem endomorphism. I told M plus that not commutative. This one also here. An example we have to for any field we are taking here. For any field we are taking here. F modules over F we are taking here are called vector spaces. In this one vector space also we can field is the vector place, and F is also called also vector space here. Any ring R can be related as an R module with respect to addition and multiplication also R. We know that here. Suppose let Rx be the set of uh, with the set of all polynomials coefficients coefficients in R indeterminate indeterminate. So then R of X is an abelian group with respect to the usual addition of polynomials. Polynomials for any A belongs to R, we are taking here. This A1 belongs to R of X, I'm taking here. A of X of X input I'm taking here. A0, A1X, A2, A1X. See here, this is A1 means X, A8, 3, X cube, A4, X power 4, A4, X4. But the abelian group of the condition is satisfying here, we can write it. So these conditions are satisfying of X, so therefore R of X is a module we are writing here. One definition. Definition. Let R be any ring and M or module. Let R be any ring and M then any module here. M is said to be R algebra over the left module or algebra over R. There is a binary operation of multiplication and addition. So we can write here M plus comma dot. is the ring which needs to be not commutative already I told. They have to a plus b equal to b plus c or that is satisfying the property. I'm writing a into xy is equal to a x into y is equal to x into a. This is a multiplication process. Find all a belongs to r for all a belongs to r, that is x comma y belongs to m. We are taking here this submodules we have to learn here. So therefore submodules we are taking here. For submodules one definition we are taking here. Let R be a ring and M on it R be another I am and module. A subgroup of n of n comma plus is said to be an or submodule of m. Therefore Ax belongs to n for all. A belongs to R. Therefore X belongs to n. So note that here 0 and m we are taking here are always submodules here of any module m. A submodule of n of m is said to be proper that n not equal to m we are taking here, n not equal to m. And said to be a trivial of n is equal to 0. Subtrivial of n is equal to 0. We given necessary and sufficient conditions of n of m become a submodule. We can write here by the condition of the always submodule of any module of m. The, the following assertions true for any module m. We are checking here. First one, the intersection of any class of submodule of any given on or submodules. The first condition. If n and k are submodules a n plus k a plus b by a belongs to n. I am taking here. Then and b plus k. A belongs to n, b belongs to a, b belongs to k. A belongs to n, b belongs to k. Both the values that I am taking here is also on A belongs to B belongs to M, B belongs to K. We are taking here is also on our submodule of M and is the smallest submodule containing N union K. The third condition is K, L, N are submodules of N such that K subset of N is K plus L intersection L, A plus L intersection A plus L intersection M. So these two conditions we have to prove here. The intersection of the intersection of the any class of the R modules is the image again R submodule. M and K are R submodules of Q. So if L and R submodules and subset to A subset of M. So we should note that the case of the ideals, we know that the earlier theorems of the this one submodules or submodules, the conditions are satisfied here. So therefore, general submodules need not to be submodules. The conditions are earlier of group second unit we learned 2.4.3 is also the correct answer for this one. Now another one definition we have to learn here. Let M be a on R module and equal to M. Then we can define here as generator of a intersection of say n by n. Each n by n is an R submodule not x is equal to n this one. And all is the submodule generated by it. And all the module generated by it. Generated by it. Yes, this is the condition of writing. So therefore, the generator of x we are writing here. The sub-generator of x, modulus of x is a modulus of x is a submodule of m, submodule of m, and in fact, less than of equal to s is the smallest submodule of m, and the containing is s. Therefore, generator of phi is equal to 0 for any subset of m is equal to submodule of x, even only generator of s is equal to generator of s is equal to s. The following is the description of this element of in the generator of s also you can take here. Let one take theorem here. 0 20 and R module phi not equal to s not s subset of equal to m s subset of equal to m. So then the generator of s is equal to summation of phi is equal to 1 to m ai f phi by n greater than 0. ai belongs to R we are taking here, and xi belongs to a belongs to R, xi belongs to. So therefore, let n be the subset. Let proof. Let n be the see here, let n be the subset of, we know that n is a given. Right side above that you can easily prove that here, right, n is a submodule of right hand side above, you can easily prove that n is a submodule of m, and a submodule of n is a subset of n. We can take here n is contained in already we know that the submodule of content of s. So therefore, if there's the smallest submodule, you can take it here n is equal to generator of x, generator of x. So if S is equal to x, we can take in here, then we can simplify here. Generator of x is equal to, we can write here, generator of x is equal to less than a generator of x in the limit from we can write in this format generator of within the brackets x We can easily observe that here generator of x is equal to rx, that is equal to within the bracket x by x, a belongs to r. That means a r value, a should be in the r. R low, a value is ఉంటాయి. So the generator of x is called as a cyclic submodule generated by x. So now we can do that here. Let R in be ring. Let R can be considered R module over itself. In the submodules are precisely ideals of R we have taken here. Another example, we have an example we have to take here. Another example, R of x is the set of all polynomials over R. Then R of x is on R module. When R of x is an R module, we can take care R of x is a module. So R of x is a R module, then we can know that R of x is a module. Any ideal, we can take any ideal of R of x. Any ideal of R of x is an R of x is a submodule. R of x is submodule. So you can know that the R of x is module or it's module. R of x is submodule, then R of x is also submodule. But in fact, we are taking the subring of Rx in R is any subring of R of x we are taking here. Any R of x submodule in submodule, therefore R of x is on R of x on R submodule we are writing. So why? Because I am telling again R module is Rx module, Rx submodule is R submodule. If any Rx submodule is Rx submodule, but that is a subring. R is a subring of Rx in its Rx module or submodule. Where there are R submodules are not Rx submodules. So therefore the condition we are writing here. So therefore I am writing here n is equal to f belongs to R, x by f is equal to 0, or degree of f less than or equal to f belongs to R, x is equal to 0, degree of f less than or equal to n, where n is a fixed non-negative integer here. So therefore non-negative integer here we are taking here. Degree f is the degree of the polynomial f is defined as an R. Then the coefficient of x power r is the last non-zero coefficient of. Then S is a submodule Rx module. X power n belongs to n. X power n belongs to n. We are taking here. X into x power n does not belong to n. So x power n belongs to n is the condition of it. But x into x power n belongs to n. It's not correct. Then the theory of the submodules we are taking here of a module f is analogous to the ideals of a ring. Two exceptions. On the set of the ideals of a ring, we have the binary operation ij ideals on addition operation set of intersection. What we are writing intersection I intersection j. The sum of means I plus j. So into means I dot j. The set of the submodules are also we have the ideal quotation I equivalent to j. Ecology is the ideal quotient of the ring of the this one. The limit of the product of the ideals of the ideal to the concept the submodules. So some definition you have to learn the submodules here. What's the definition of module? Let M be an R module. Let M be an R module. For any ideal, for any ideal I of R, and any submodule in of M on any submodule in of M, it is in here. Equal to 1 to say by n greater than 0. Y belongs to Y. Xi belongs to Y. Ai belongs to I. Xi belongs to M. Is if n is called here is called product of IN. IN is called product of IN. Product of IN we are writing. And the second condition we are writing is any submodules for any submodules we are taking here, for any submodules, n and k of n, the submodule ideal of quotients this one. A belongs to R by move to subset of n. So the above, this one we are writing here. Equivalence is not submodule of M. So therefore it is not submodule of M, but on ideal of R. So in particular we are taking here, but in particular we are taking here this one. So that is A belongs to R, AK is equal to 0. That means A belongs to R, that means AX is equal to 0 for all X belongs to. So we are taking here. It's called as annihilator of idea, and K is also denoted by annihilator K. We are writing annihilator means A and K. So therefore K equivalent to less than X, sorry, generator of X. Cyclic submodule generated by an element that is X belongs to M, X belongs to M and determinant. So when X, then now X I am writing here. An annihilator express of annihilator of generator of X, generator is a bracket of X. You can try to, you have to take it through the following properties of the each operator. Quotient models. Quotient models we are taking in. The quotient models also, we have to learn that in the quotient models here. The concept of the quotient model with respect to the submodule, already we learned here, submodule here. Introduced in this section. By this, we we acquainted with the concept of the quotient group of the almost quotient ring and the quotient space of the vector space. The idea is the same here also. Submodule of module, then we get equivalence relation M such that the equivalence of classes in M. Recall that the theta is equivalence relation set of M. Then X belongs to M equivalence class is defined as, you can write here. And also recall the equivalence classes part partition of M. So this one. Then the definition, what is the definition we will take here? This one, quotient modules definition. So let M be a module. Let M be a module over a ring or a binary relation. A binary relation theta on M is said to be on M the following circle. See here. Let M be a model over ring R, a binary relation we have to set the congruence following set. Zero is equivalence relation on it. Zero is equivalence relation. Zero is equivalence relations to M. First of all, equivalence relation on M, x comma y and u comma v belongs to theta. X plus u and y plus v belongs to theta. X plus u and y plus v are taking it. Third one, x comma y belongs to theta. That means ax comma ay belongs to theta for a belongs to these conditions are satisfying here. So for a model, the congruence and submodels are in one-to-one correspondence. We shall the following other theorems with these conditions are satisfying or not. We can use this definition. Over the ring R for any submodule n of m. For any submodule n of m, the relation theta n, defined as theta n x comma y belongs to m into m, that is x minus y belongs to m. So x comma y belongs to m, we are writing x minus y belongs to m. So in this congruence of m, we are taking here of m. Conversely, congruence on theta n is theta n for some or submodule n. We can theta of 0 is equal to n and theta of x is equal to x plus n. We are taking here for all this is x belongs to n. This is all the statement. I am written the statement here. Theta is equal to x comma y n into m, y x minus y belongs to m. Theta is equal to 0 to x x plus n for all x belongs to m. Then proof I am taking here. Suppose n is on n is on our submodule. Suppose n is on submodule of m, we are taking here. If n is on our submodule of m, we are taking here. We have to prove that theta n is m. For every x belongs to m, I am taking here. So x plus x is equal to 0. X plus x is equal to 0 belongs to m. The condition is satisfied. Therefore, x comma x belongs to theta n. Y is equal to theta n. Reflexive. Reflexive here. Then for x comma y is equal to theta n. Then y minus x is equal to minus. I am taking the form minus x into minus 2. So this is a minus x into minus y. So plus minus x minus y belongs to n. And hence minus x and minus y belongs to n. And y comma x belongs to theta n is symmetric. N is symmetric. Therefore x comma y I am taking here. Y comma z. X comma y comma z we are taking here. X comma y comma z belongs to theta and I am taking here. So therefore, what is the condition here? X minus z is equal to what we are writing? X minus y plus y minus z. Why? Because plus and minus are cancel. For x minus z, it belongs to m. Therefore, Hence we are taking here x minus z belongs to theta n. So that is theta n stands to theta tends to plus theta is so the theta n is equivalence relation of m. So therefore if x comma y if x comma y is equal to uv belongs to theta n. So x plus u minus y plus v. So therefore x plus equal to what I am taking here x minus y I am taking here x minus y plus u minus y I am taking here this one u minus v. This x minus y and u plus v, that is a separate one I am taking here. Hence x plus u y plus v belongs to theta n. So ax minus ay ax into x minus y ax ay belongs to theta n. So therefore theta n is congruence of m. We are taking it. So therefore conversely we are taking here suppose theta is uniform. Suppose is any ten is equal to 10 theta is equal to 0, therefore x belongs to n. X belongs to 0, 0, 0. Then but you can check that n is on submodel. Then R is submodel we are taking here. Okay. Also we are taking here x comma y belongs to m here. So x comma y belongs to theta belongs to theta. Since we are taking minus y and minus y belongs to theta. X minus y belongs to m. Therefore that is x comma y belongs to theta. X comma y belongs to n. Plus theta is equal to theta n for any x belongs to m. Y belongs to theta of x I am taking here. The condition is x comma y belongs to theta. X comma y means x minus y belongs to x minus y belongs to n. So therefore x comma y belongs to n, also y minus y belongs to n also are taking here. But the condition is satisfying here. Y belongs to x plus n I. Y belongs to x plus n I. Therefore theta x is equal to know that x plus n. The condition is satisfied. And the with Indian or module. Let M be an R module. Every instance to Pn is a one-to-one corresponding. To the set of all and the set of concurrence. So therefore, let M be an our model then instance to theta n is the one-to-one correspondence between set of submodules and such a correspondence m for any of our submodules and k. Theta n intersection k is equal to theta n intersection theta k, and theta n plus k is equal to theta n circle theta k we are taking here. So hence the two congruences of the m premium, that is theta circle of phi is equal to phi circle of theta. Theta circle of phi is phi circle of theta, which is how to prove. Let n indicate any R submodule of n or any xy comma belongs to n for any x comma y belongs to n, we are taking it. X comma y belongs to the intersection k. X comma y belongs to intersection k. X comma y belongs to n. X comma y belongs to k. X comma y belongs to n. X comma y belongs to intersection k. And for x comma y belongs to theta n intersection theta k. X comma y belongs to, that is x comma y belongs to x minus y belongs to k. Both the conditions are taken. X comma y belongs to n. Theta n intersection theta k, both the values is there here. And hence theta n intersection k is the base. Theta n intersection theta n reflects n. So n is equal to theta n in the intersection that one condition theta intersection theta k, theta n subset of theta k n is equal to theta n subset of theta is equal to k, the condition factor. So therefore instance to theta n is 1 to 1 and 1 to 1. We know that the earlier theorems also. This is map is 1 to 1 and on to also. Here we are so providing here theta n plus k here. Theta n subset of theta k. So theta intersects something theta k. Where since we are taking again k subset of n plus k, so k subset of n plus k, we can take theta k subset of theta n plus k. So we can take the theta k subset of theta n plus k. So and since theta n plus k we are taking here the transistor. What the transistor here? Theta n plus k, theta n circle theta k is equivalent to the theta n plus k. Theta 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 n intersection theta k subset of equal to theta n plus k. The condition is satisfied here. But even though condition has been, you can take your letter that x comma y belongs to theta n plus k we are taking here. So then x minus y belongs to n plus k. So this value is in the n plus k and n plus y belongs to the k and x minus y is equal to u plus k. But some u belongs to b and the b belongs to k. So therefore z is equal to y plus u. I am taking here z is equal to y plus u. So z is equal to y plus u means what is that? U belongs to n and b belongs to k, z is equal to y plus u. And x belongs to z is equal to x belongs to z is equal 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 to y plus u. I am taken here. So z minus x belongs to z, x minus z, sorry. X minus z is equal to b belongs to k. And z minus y is equal to u belongs to n. So and x minus z belongs to theta k. I am writing here. So z comma y belongs to theta n. So this implies that x comma y belongs to theta n, circle of theta k. So therefore theta n plus k, theta n circle of theta k. So these therefore the theta n plus k subset of theta n circle k are earlier we told here, or theta n circle theta k subset of theta n plus k, both are same here. For this one we have taken here, uh, and hence here both are equal here. So theta and phi are congruence of the m. So theta is equal to theta m and phi is equal to phi of k. So are submatrix of k, and therefore theta m circle theta k is equal to theta m plus k is equal to theta k plus n. Both the values are same, k plus n, k m plus k. So is equal to theta k circle theta m. So this is also same. This is also same here for this one. So therefore phi of circle of theta. So hence theta and phi are permittable here. Hence theta and phi are permittable here only. So this one from the congruence of the module of this submodule, I guess it will be theta theta 0, so theta n is m. And this is the module structure of the set of equivalences to the x of x plus n given this one, the submodule 4. Another one we have to learn. Let n be on our submodule of or module m by n plus n by x belongs to m by n means x plus n by x belongs to n we are taking here. This is defined what is the expression here. Y plus n belongs to, if this value is in the m by n and a belongs to r we are taking here. So x plus n and y plus n, this is statement I am writing. So x plus y plus n, I am taking the common x plus y plus n is equal to n into x plus n, ax plus n. Therefore, n by n is our module we are taking here with respect to the these operations we are taking here. These operations we are taking here. Now proof we are taking here. First, we have two processes. Two processes I am taking here. Two processes of n. are either equivalent or disjoint. Round 6 belongs to M, X plus N, Y plus N. So X plus N is equal to Y plus N, that is X minus Y belongs to N. So we know that the condition, the operations are, we know that this M by N is well defined, we know that. M by N is well defined, but X plus N and Y plus N is also, we can write here in the associative X plus Y plus N and taking the common of N, X plus Y plus N. So it is the link of the depending of the elements X and Y, but we can easily, depends upon the courses here X plus N and X plus N, Y plus N, but not both and X Y. If by X not, Y we are not taking X plus N, Y plus N, we are taking here. Xn but not it. So the details of uh, this one. So therefore n is equal to zero plus n is a zero element, that is m by n. So therefore x plus n comma minus x plus n is the additive inverse of, so x plus n minus x plus additive inverse, you know that. So therefore it is the inverse of x plus n, we can take here. For any R module, n of on R module, yeah. So see here, for any R module, N R for R module, N of R module M by N is described above is called the quotient by M by N. So in the one theorem we have to learn here. Let M be an R module, you can take in here, and N R the submodule. For any R submodule, we are taking K of M containing. So we are taking here, let M be an R module, submodule we are taking here. In containing N, K by N is equal to X plus N by X belongs to the, then K by N is, then K by N is a submodule of the quotient module. K by N is a submodule of the quotient module of K by N, you know that. I'm writing that. K by N. K stands to K by N is a 1-to-1. what is maintaining in the submodules. Submodules you are taking here m by n. K1 subset of K2, that is K1 by n subset of K2 by n. So K1 subset is equal to n into K1 subset K1 by n subset K2 by n. For any or submodule, for any or submodule, they are containing clearly A by n is a submodule. So K1 is submodule you have taken here. That one in the proof. For any or submodule, K1 is a submodule. Submodule, so therefore, submodule of n by n we are taking. K1 can be submodule. Submodule of containing n. K1 subset of K2 equal to K1 by n equal to K2s. And the other way, 1 by the K2n, K1 by n subset of K2 by n. X belongs to K1, X plus n belongs to K1 by n subset of K2 by n. We are taking a K1 by n and K2 by n. So we take X plus n is equal to y plus n for some y belongs to K2. Y belongs to K2 we are taking here. x minus y belongs to n we are taking here, and y belongs to k2 also. X belongs to n, x by y belongs to k2. Plus y belongs to n plus k2 I'm taking here, therefore k2 is equal, therefore n subset of k2 I'm taking one subset of k2. Because that k by n is 1 to 1. So prove that this is 1 to also, therefore k dash you get to n by n takes me here. K is equal to x belongs to n, x belongs to this k belongs, k dash means k dash values x plus n in the cell taking here. So therefore x plus n belongs to k dash we are taking here. So any zero element by m by n, k dash is being submodule of m by n should contain the zero element. So m plus of complements of. So this is the, so what is the condition here? K is equal to x belongs to m, x plus n belongs to k dash also here. X minus y belongs to n, y belongs to 2. X equal x minus y plus y belongs to k2. So n subset of 2. These conditions are satisfying here. So therefore third n subset of equal to k. The condition is satisfying here. So another theorem or theorem we have to learn here. Let m be, let m be a and let m be a normal. Ideal of r and the n of the body and from such that then n by n then n by n can be considered as a r by I module by defining a plus I plus m expression. So this is the expression I'm taking here. Which I'm taking here. First we have to, these operations are well defined. A comma belongs to m for x comma will belongs to m. So a plus I is equal to b plus I. So therefore x plus n is equal to y plus n. So this is the commutative expression is equal to y plus n. A minus b belongs to y, then x minus y belongs to also. Yeah, these conditions are satisfying here. And hence a minus b belongs to x belongs to I'm taking here b into x minus y belongs to n. I'm also taking here. So therefore ax minus by is equal to a minus b into x. A minus b x into b into x minus y. I'm taking the common here. A minus b into x minus y belongs to n. So therefore ax plus n plus n b by plus n. So this operation is well defined here. So this for m by n is and r by I is r by I is model. Then homomorphism. So what is the definition I learned here? Let R be a ring. Let R be a ring. Let R be a ring and the M and the M be models over R. A mapping of n to n, a mapping of n to n, so the homomorphism of following was satisfied. That was the condition of x plus y is equal to the f of x plus y. I am writing here for all x comma y belongs to M. So f of ay is equal to of f of x, a of f of x, yes, and so therefore a of x taking the for all a belongs to R, x belongs to. So therefore, and on R on R is a homomorphism. So therefore, f n stands to f of n stands to n, and on R modules we are taking is primary homomorphism. Is homomorphism the group of n plus n comma plus into n comma plus. You can easily check that f of n come n to n. So this is a homomorphism if only f of x plus f of x plus b of y. For all a comma b belongs to one, I'm taking here x comma b belongs to one. To this one, the condition is satisfied. So it is a of corresponding of the inner homomorphism. So this one is proving. Any doubts, ask me. I will clarify.